Hey there, future doctors and engineers. Welcome to a power-packed revision of one of the most important and, let's be honest, often trickiest chapters in Class 11 Physics, rotational motion.
I get it, I really do. This chapter can seem a little tricky, right? But hey, don't you worry. We're going to break down the most important concepts in a super simple way, so you can walk into your exams and just nail those questions with total confidence.
All right, let's kick things off with our first big idea, the center of mass. Just think of it like this. It's the magical balance point of a system. It's that one spot where we can pretend the entire mass is concentrated. You know, kind of like how a tightrope walker uses that long pole to find their perfect balance. That's the center of mass in action. So if we want to get a little more formal about it, the center of mass is the mass-weighted average position of all the particles. Now, what in the world does mass-weighted mean? It's actually super simple. Think about a seesaw. The heavier person has a much bigger effect, right? Well, it's the exact same idea here. The heavier particles in a system have more influence, more pull, on where that final balance point is located. Okay, let's tackle a typical exam question. We've got 3 particles here. First things first, step 1. You always want to place them on a coordinate system. Makes life so much easier. Then, for step 2, to find the x-coordinate, we just plug everything into that weighted average formula. See how we're multiplying each mass by its x position, adding them all up, and then dividing by the total mass? For step 3, you guessed it, we do the exact same thing for the y-coordinate. Just follow these steps carefully, keep your calculations neat, and I promise you'll land on the right answer every single time. All right, moving on, let's talk about the real stars of rotational motion, torque and angular momentum. And here's the good news. If you've already wrapped your head around force and momentum in linear motion, this is going to be a breeze. Seriously, just think of torque and angular momentum as the rotational cousins.
Okay, this slide right here, this is your ultimate cheat sheet for this chapter. I mean, just look at that beautiful symmetry. Everything you know from linear motion has a direct counterpart in rotation. Force becomes torque, mass becomes moment of inertia, linear momentum becomes angular momentum. Even Newton's second law translates perfectly. This is the absolute key to the whole chapter. The physics doesn't change, just the language we use to describe it. If you get force, you'll get torque.
So what is torque, really? Well, in the simplest terms, it's a turning force. Just picture opening a door. If you try to push it open right next to the hinges, it's really hard, isn't it? But if you push on the handle, way out at the edge, it swings open easily. That's torque. In the formula, that R is the distance from the pivot point, the hinge. The bigger the R, the bigger the turning effect you get for the same amount of push. All right, now let's meet mass's rotational big brother, moment of inertia. You know how mass is all about resisting a change in linear motion? Well, moment of inertia does the exact same thing for rotational motion. It's a measure of how much something resists being spun. Basically, it tells you how difficult it is to get something rotating. Now here's the crucial part. Moment of inertia isn't just about how much mass you have. It's about where that mass is located relative to the axis of rotation. This is huge. Mass that's farther away from the center contributes way more to the resistance. In fact, because the distance r is squared in the formula, if you double the distance of a piece of mass from the axis, its contribution to the inertia goes up by 4 times. That's why mass distribution is absolutely everything here. Okay, guys, this table is super important for NEET and JEE. You've got to memorize these formulas, but look closer. Notice how a thin ring has a larger moment of inertia than a solid disk, even if they have the same mass and radius? Why is that? Well, think about it. In a ring, all the mass is far away from the center at the maximum distance r. But in a disk, the mass is spread out, all the way from the center to the edge, kind of like the blaze of a ceiling fan. That's why the ring is harder to spin. And this brings us to one of the most beautiful and elegant principles in all of physics, the conservation of angular momentum. It's simple. If there's no external torque acting on a rotating system, its total angular momentum, L, stays constant. And since L equals I times omega, well, let's see what that means. Imagine a figure skater spinning with her arms stretched out wide. Her arms are far from her body, so her R is large, which means her moment of inertia, I, is also very large. Okay, now watch the magic happen. As she pulls her arms in, she's bringing all that mass closer to her axis of rotation. So what happens to her moment of inertia, I? It goes way down. But remember, the total angular momentum, L, has to stay the same. So if I get smaller, what has to get bigger to compensate? You got it, her angular speed, omega. And suddenly she's spinning much faster. It's the same principle a cricket bowler uses to put a wicked spin on the ball. All right, our next topic is rotational equilibrium. In physics, the word equilibrium just means no change. It's a state where an object's linear motion isn't changing, and its rotational motion isn't changing either. It's just perfectly calm and balanced. And to achieve this state of equilibrium, there are just two simple conditions you need to meet. First, the net external force on the object must be zero. That means no linear acceleration. Second, the net external torque must also be zero. That means no angular acceleration. That's it. Just remember those two rules and you can solve pretty much any equilibrium problem they throw at you. So let's apply these conditions to a classic problem. We have a bar supported on two knife edges. Step 1. And this is always step 1. Draw a free body diagram. Show every single force, the upward reaction forces R1 and R2, and the downward weights W and W1. Step 2. Apply translational equilibrium. This means your total upward forces have to equal your total downward forces. Step 3. Apply rotational equilibrium. Pick a pivot point. Any point works, but the center of gravity is often a good choice. And make sure the total net torque is 0. Step 4. Now you've got two equations and two unknowns. Just solve them simultaneously to find R1 and R2. Done. All right, let's wrap this up and summarize the entire chapter on one final slide. These are the absolute must-know formulas that you need to have at your fingertips. Okay, let's lock these in. Center of mass, your weighted average position. Torque, the turning force. Angular momentum, the amount of spin an object has. Rotational kinetic energy, the energy it has because it's spinning. And finally, Newton's second law for rotation. Torque causes angular acceleration. Go ahead, take a screenshot of this. This is your ultimate last-minute revision tool. And there you have it, a quick tour of rotational motion. I really hope those key concepts are feeling a lot clearer now. But before you go, here's a little something to think about. We saw that the skater spins faster when she pulls her arms in. Her rotational kinetic energy increases. But where did that extra energy come from? Give that some thought. If you found this explainer helpful, please hit that like button and be sure to subscribe for more explainers like this one. All the best for your exams.